the next rotational topic we're going to look at is torque. And I'm sure you've heard of torque before, especially in car commercials. We're going to look at now what torque actually is and how that applies to physics. Okay, so before we look at torque, you need to know that a pivot is the axis about which an object can rotate. So when we were looking at rotational kinematics, we were just looking at an object as a whole, say rolling down a path or turning in a circle. Now we're going to look at the nitty-gritty of all of that and what actually causes the rotation. So just like a force caused an object to accelerate or to change what it was doing, a torque is going to be the equivalent of that in the rotation world. So a torque is going to cause an object to rotate. Torque is positive when it's going to rotate counterclockwise. So just like with angular velocity, angular displacement, positive is counterclockwise, and it's negative when it tends to rotate the object clockwise. So the symbol for torque is the Greek letter tau. It's kind of like a cursive T, and the unit for torque is the Newton meter. I know that's the same unit of energy, but torque is not energy. So torque's unit is a Newton meter, just like energy, but it is not a joule, if that makes sense. So symbol tau, unit Newton meter. And just looking at this diagram. So here's a pivot point of, say, a wrench. It's going to rotate, so if this force is applied this way, it's going to rotate that way. So this would be a clockwise torque, which means it would be negative. When we get to the equation for torque, the equation for torque is going to relate this angle right here, the radial line, which is just where the radius is, and the force. So keep this picture in mind. Okay, the ability of a force, so in other words, the ability of torque to cause rotation is going to depend on three things: the magnitude of the amount of force, the distance from the pivot to the point at which the force is applied, and the angle at which the force is applied. So the equation for torque, T is going to equal the force times the radius times the sine of the angle. I prefer to use, where is this? I prefer to use phi instead of theta. So you might see FR sine phi. It's the same idea as when we did work. If you remember, work was FD cosine phi, but your formula sheet gave theta instead of phi. You're going to see the same thing with torque. So the angle phi, let me just define what all of these are, or theta in this case. It's the same angle, is the angle between the force and the radius. Just like when we had our work diagrams, so remember the work diagrams, you showed the direction of the force, the distance, and then phi. Same idea here. So you're going to have your force, say you have your radius, this would be the angle theta or phi. And you'll see me switch between theta and phi, but just know that your formula sheet gives theta. This is the distance to the pivot. Or radius. This is the force. And then that's torque. You will also see on your formula sheet this equation. T equals F R and that little symbol right there. All this means right there is perpendicular. So the rest of the formula on the equation sheet is FR sine theta. The reason we say perpendicular, you can only have a torque by a force that is perpendicular to the radius of the object. So let's say we've got an object here and this is the pivot. And if I try and apply a force in that direction, nothing's going to happen. So this is parallel. This force is parallel to the radius. Nothing's going to happen if you're going to push on it. That won't cause rotation. Think of it this way too. Sine of either 0 degrees or sine of 180 degrees equals 0. So you will have no torque if the angle between the radius and the force is either 0 or 180, meaning it's parallel. If you have a force that's, say, in that direction, I'm just going to redraw it up here. So here's your force. This is the radius. This is the angle theta. What you're looking at is really the perpendicular component. So when it has this, when it has this perpendicular sign, what it means is you're looking at the y component of the force, which the y component of the force is the force times the sine of the angle, which is where the F sine theta comes from. So I'm not really going to worry about this part from your equation sheet. We care more about this right here because the F sine theta will get you the perpendicular component, if that makes sense. Okay, so once again, torque equals FR sine theta. Theta has to be relative to the x-axis or the radius. It doesn't necessarily have to be x-axis. If I have an object like this, and we've got a force applied this way, this would be theta. So theta is between the force and the radius of the pivot. All right, let's do an example. Ryan is trying to open a stuck door. He pushes it at a point 0.75 meters from the hinges with a 240 Newton force directed 20 degrees away from being perpendicular to the door. I know that's a little wordy. There's a natural pivot point, which is the hinges of the door, and we want to know, A, what torque does Ryan exert, and B, how could he exert more torque? You want to draw torque diagrams just like we used to have force diagrams. The difference between a torque diagram and a force diagram, the force diagram always had a point and it showed all of the forces coming out of that point. A torque diagram will be the shape of the object, where the pivot is, so that's not the point, where the pivot is, and then the direction of the forces. So in this case, your torque diagram is going to look almost exactly like the actual diagram. So our torque diagram is going to look like this. We have our radius, which is here, our force, which is here. So the angle theta is that one right there. If you look at the diagram that it gave us, the angle theta is actually right here, meaning if this is 20 degrees, then theta is equal to 70 degrees. So the trickiest part about torque problems is making sure that you're getting the right angle. So now let's list what we know. It tells us that the radius is 0.75 meters. He's applying that force 0.75 meters from the pivot. That the amount of force is 240 newtons. And theta is 70 degrees. We're looking for torque and then how he could exert more torque. So simple equation. Torque equals FR sine theta, 240 newtons times 0.75 meters times the sine of 70 degrees. And this equals 169.1, keeps on going, your units, Newton meters. 1 sig fig. The torque is about 200 Newton meters. And because this is rotating counterclockwise, so if we look at the way the force is pulling on it, this is going to cause a counterclockwise rotation, then we'll leave this as a positive torque. Okay, so our final answer would be 200 Newton meters. Oops. Make that a little thicker. So 200 Newton meters. And again, if it was going the other way, then we would have to make that negative, but that all depends on the direction of the rotation. I'll do one more example if you want to watch it. If you feel okay with this, then you can stop there. Okay, so the next example, revolutionaries are attempting to pull down a statue of the great leader by pulling on a rope tied to the top of its head. The statue is 17 meters tall, and they pull with a force of 4,200 newtons at an angle of 65 degrees to the horizontal. What is the torque they exert on the statue? And if they are standing to the right of the statue, is the torque positive or negative? So let's draw a picture. Here is our statue on the ground, and then you have the people pulling down the statue from a rope tied to its head. So if I list what we know, and this is at an angle 65 degrees relative to the horizontal. So our given information, the statue is 17 meters tall. We're going to assume that the pivot is down here. If you're pulling from the head of the statue, it's going to rotate this way. So from the head down about this point right here. Okay, so we are given that the radius is 17 meters. The force is 4,200 newtons. And the angle. So remember, it's always the angle between the force and the radius. So looking up here, it wouldn't be 65 degrees. Theta would be 25 degrees. We are looking for torque and whether it's positive or negative. Okay, so let's draw our torque diagram. Let's just assume that this is the statue. It's essentially a line. Here's the pivot. Here's where the force is applied. The angle between the force and the radius is 25 degrees, and we know that our radius is 17 meters. Torque equals Fr sine theta. So this equals 4,200 newtons times 17 meters times the sine of 25 degrees. And that's going to give us 30,174.94, keeps on going, Newton meters. So the torque is approximately equal to, and this is also asking, is it positive or negative? Because this is rotating clockwise, the torque is about negative 3.0 times 10 to the fourth Newton meters. If I drew my picture the other way, then it would have been positive. So if I had my force going this way instead, then it would have been a positive torque because it would have been going counterclockwise. That's why if it doesn't give you a picture, you need to draw one. All right, so that's about it for torque. We'll do a little bit more practice tomorrow, and then we'll see demos and actually be able to feel how the torque applied to objects causes the rotation and what changes that.